Okay, so welcome everyone to Bilecik Algebra Number Theory and Seminar. We are very happy to host Professor Ariel Pacetti from University of Aveiro, Portugal, and he will speak about hypergeometric motifs and Galois representations. Thank you.
Okay, so let me start. Thanking Ike for inviting me to give this talk. So I'm going to talk about infantile problems and the hypergeometric motifs will appear while talking about it. So I'm going to be a little more classical, so it's going to be sort of like a blackboard talk. So if you have any questions or things like this, I don't know exactly how this work. Ike, maybe you can ask them on the chat or raise your hand or something. I'm sure someone would moderate this. So somehow the goal is to try to understand the solutions of the generalized Fermat equation. So the classical Fermat equation is, you consider the equation x to the p plus y to the p. I'm going to write plus z to the p equals to 0. This is not exactly the classical Fermat equation, but if you assume that exponents are odd, then that's okay. You can just put the minus sign via change of variables. And so how does the proof given by Wise and co-workers worked? So what is called somehow called the modular method works as follows. So it should be a 1 here. So you start attaching some geometric object which has nothing to do a priori with the solution. So you consider phrase curve, phrase or phrase Galois curve. And I want to record the equation. So I'm going to denote it E, which depends on the parameter Z, which is y squared equals x times x minus 1 times 1 minus zx. Okay, so the point is that this object it only depends on the exponents, and we will see that this is a general strategy. It doesn't depend so far on the solution. And then you say, let's start with the solution. So let A, B, C be a solution to the equation. Let's call it 1. And then what you do is you specialize at a point which does depend on the solution, which is minus A to the P divided by C to the P. And that's more or less what you want up to twist. And the main result of this, so the key fact, is that if you consider the Galois representation of the specialization at the prime P, and you look at the residual image, I'm going to say a little bit about what this is, then this representation is unramified outside 2. Okay? So what does it mean, the representation? So when you have your elliptic curve is like a torus, the complex points. So you can look at the p torsion points. So you can look at the points which satisfies the equation. And maybe I should write it, call it Q. And satisfies that P times Q equals to 0. It has the structure of a group. This is what we usually call the P torsion of the curve. So since the curve has such rank equations, these points are rational. It's given by a rational equation. And what happens is that as a group, this is just 2 copies of Z mod P. Okay? And this fancy thing here, what it's only saying is that since the point has algebraic coordinates, you have the Galois group of Q bar over Q acting on them. And this gives you a 2-dimensional representation. And this is somehow the representation that you're considering. But another way of stating this is that if you join to Q all the P torsion points of this elliptic curve, the specialized one, this is going to be an extension of Q, which only ramifies at 2. See somehow there is some ramification at P, but pretty much the ramification at P comes because you're considering the P torsion point. But the point is that you got rid of all the other primes and you're constructing extensions with very little ramification. This is somehow the strategy on the background. And somehow the point is that if you'd like to, in a way, try to construct abstract extensions of Q, which ramifies only at a few primes, it's extremely hard to do that. The Galois group is going to be a subgroup of GL2 of FP. Then you can think just this of like an abstract problem. Let's suppose I want to construct extensions of Q, whose Galois group is a subgroup of GL2 of FP. Most of the times it's going to be the whole group, and with very little ramification. And we don't know exactly how to do these sort of things. But here is the second key step. So this is like the first, that you have very little ramification. The second key step is that actually the elliptic curve is modular. So modular means that it is related to an object, a modular form, for some level that can be computed. But the key fact of this is that this is a finite dimensional vector space. So you can compute this. You can put it in a computer, and actually a lot of implementations, there are databases. You can use Magma, you can use Sage, and you can compute these spaces. So somehow this is like the world that you like to try to construct. You like to construct this sort of extensions, and we don't know how to do this, but you relate these extensions to something that can be put in a computer. The problem is that here, the level of this form depends on the solution. So N depends on A, B, and C. So this is not good because you want to prove whether there is a solution or not. So you cannot have to compute spaces that depend on the solution. And then the third big step in this theory is a result of Rivet, which somehow what it's telling you is saying, well, the modular form, since the Galois representation modulo P has very little ramification, it's unramified outside 2, and of course P, then this has to be congruent to another representation, which also comes from a modular form. Let's call it G. But G has level a power of 2. Okay? So somehow it's like what you attach naturally to a solution is these extensions of number fields. So it's a finite extension of Q with very little ramification. And since we don't know exactly how to characterize these extensions, then we start to try to match it to different geometrical, to different objects, analytic objects in this case, that we can try to compute in a computer. So the residual one, we are using some argument, which is lowering the level result of Rivet, to match it to another modular form whose level is in the complete independent of the solution. And furthermore, what you can prove in this case, if you start with a solution such that B is even, then the level of G is exactly 2. Okay, so you have to make some choice. It's not true that any solution will have level 2. But if you assume that B is even, you can always permute the solution, the coordinates A, B, and C. Then you can assume that the level is 2. And how do you prove? And the proof, you're saying, okay, the space of weight 2 and level 2 modular forms is just 0. So there cannot be a form, end of the story. So there cannot exist any non-trivial solution. There is a little catch here. If you start with a trivial solution is one where one of the coordinates is 0. So if A, B, or C is 0, what happens is that the elliptic curve becomes a singular curve. So it's no longer an elliptic curve. So that's how somehow you can get rid of these nasty solutions somehow. You can always put like A minus A0 or A0 minus A or 0A minus A, but it's going to give you singular geometric objects. So that's somehow how you can get rid of them. And so what I'd like to say a little bit is, you see, this is not the classical approach. Actually, you have to do a twist of the elliptic curve to get exactly fair curve. So what I'm writing is exactly true up to a quadratic twist. This is not the original approach of how it's presented most of the times. You just find an equation and you don't see it as a specialization of any family. But this is somehow the idea, the underlying idea that Darmon described in his program. So the underlying idea of the proof is the following. When you computed your specialization, which is going to be minus a to the p divided c to the p, it has the following properties. The numerator is pretty much a pth power up to a sign, but it's pretty much a pth power. The denominator is also a pth power. And if you compute 0 minus 1, this is exactly minus a to the p minus c to the p divided c to the p, which is exactly minus b to the p divided c to the p. So 0 minus 1, the numerator, is also a pth power. You see? So what this is telling you is that if you think of your parameter, then when the parameter somehow is trying to reach 0, it's like a pth power. When it's trying to go to like infinity, it's like a pth power. And when it's trying to go like to 1, it's also a pth power. Okay? And the idea is the goal is to construct extensions of, let's say, Q of Z, where Z is a variable, which has somehow like with particular behavior at 0, 1, infinity. And what do I mean with particular behavior at 0, 1, and infinity? And this is somehow the key of the story, is that if you consider, for example, the extension Q of taking the pth root of Z, and then you specialize at a point which is a pth power, I don't know, 3 to the p, then the extension is going to be ramified at 3. You see? So somehow, when you say particular behavior, you like to have extensions where the ramification at 0, 1, and infinity have to do with the powers you get when you specialize your parameter. This is somehow the whole idea behind this strategy. And what you really would like to get is, instead of getting an extension, you like to get the extension to be obtained as a Galois representation. So you like to get a Galois representation, let's say from the Galois group of Q of Z bar divided some field to GL2. And here I'm going just to be a little, I'm not going to give to say exactly which field you want. I will come back to this in a few minutes. Satisfying that when you compute the inertia at 0, you like it to be somehow of, ideally, of order P. Inertia at 1, we like ideally to be also of order P. And inertia at infinity of order P. Okay? And the idea is also the same. Let's suppose, for example, that your inertia at 1, why do you want this sort of behavior? Because when you specialize the parameter, when you do at your parameter, what you're going to get somehow is like of order P. What I mean is that it's generated by some matrix, and this matrix has order P. So what you're going to get when you specialize is you're going to get like this matrix raised to some power. And I want to be a little more specific with this. So let me just try to go a little bit into Darmon's program. So the idea in Darmon's program is to put here a finite field. So you aim to construct a representation from the Galois group of Q of Z bar over F of Z, where F is a number field. So it's a finite extension, and you want to lie into GL2 of a finite field of characteristic P. Okay? Such that you want, when you compute the image of inertia at 0, has order P. I want to write it, okay, has order Q. Let me just write it down, and then I explain where it comes from. Has order P. And when you look at infinity, has order R. So why do I want 3 different exponents? So the goal is to study the generalized Fermat equation. So you start with 3 different exponents, x to the q plus y to the p plus z to the r equals to 0. Okay? A priori, the 3 exponents might be anything you want. And then you see, if you start with a solution, then you will specialize at minus a to the q divided by c to the r. So now the numerator is a qth power, and the denominator is an r power. So that's why you want some flexibility on the orders that you put at 0 and at infinity. And if you take the difference, see, not minus 1, what you get is minus a to the q minus c to the r divided by c to the r, which is minus b to the p divided by c to the r. So at 1, somehow you'd like to get something of order 1. Okay? And you search for a representation like this, and the conditions you like to have, something of order q at 0. This is actually in Darmon's articles as the projective order, but that's okay. So up to elements in the center, but it doesn't make any difference. I mean, you can just twist. You want this condition at 1, and you want this condition at infinity, and then you have to impose 2 other conditions. This field, the field F, which is going to be called the field of definition, the field F should be independent of the prime P. And the last condition you want, which is a technical condition, you want things to be rigid, so you want the determinant to be fixed. When you restrict to the geometric part. So let me just give you a hint of what's going on here. And so we start, when you consider the general Fermat equation, in general, what happens with the modular method is the following. You really like to understand this equation for any triple of parameters, Q, P, and R. It's a completely open problem. Understand this, and it actually has a huge price behind. So you like to take any 3 numbers, Q, P, and R, and try to see whether it has a solution or not. When you want to apply the modular method, in general, what happens is that you can only vary one of the parameters somehow. Okay? So you can think like you have a 3-dimensional space, and then you have to choose a line beside this 3-dimensional space. Okay? And the reason somehow is because these conditions that you're trying to impose, you cannot impose them, all of them, in a global representation. You can only impose them in a local representation. So there is no global object which satisfies these three properties. This is an explanation why you cannot aim for a general phenomena. And so you see what you are going to try to do is say, okay, let's suppose that I fix two of the three exponents, Q and R, and I'm going to let the third one to vary. So for example, I can say I would like to understand the family of Galois representations 5PR, 5P3, for example. Okay, so I fix two of them and I leave one of them to vary in families. Okay, so when you do this, then the vary parameter is going to be the one that has to do with the residual image. So here is the P, somehow. And then the field of definition, you want it only to depend on the other two coefficients because you want it to be fixed. You see, in the case of the classical Fermat approach, you really want to compute modular forms, classical modular forms. But in this case, the modular forms are going to be modular forms defined over F. So if you want to do a finite computation, you need something to be fixed. So you want always to be working on the same number field and with a particular level, so you can go ahead and do the computation. And in this particular case, when you have these three parameters like this, your field F, it's not only going to be independent of P, but it's going to be Q of CQ plus times Q of CR plus. So it's a composition of the totally real subextensions of the cyclotomic fields. Okay? So this is what Darmon proved in his article, that you can construct such a representation. And what is the goal of, what do you want is the representations? Because under this hypothesis, then the big result is that when you specialize, if this representation exists, when you specialize that a solution has, once again, very little ramification. So now it's going to be an extension of F. Here you have the kernel of this representation. It's going to be pretty much only ramified at Q and R. And of course, there is some ramification at P because you're considering a representation modulo P. But when you want to compute spaces of modular forms, somehow, like the good part here is that your representation, the ramification is really, really small. It's really bounded. That's the main point here. But there are a lot of issues with this approach. One of them is that, once again, we don't know how to construct extensions which are only unramified outside two places or something like this. And then we would like to somehow to relate this to a modular form, which is something that we can still compute. Now, it's not going to be a classical modular form, but it's going to be a Hilbert modular form because this field is totally real. So somehow the idea is that, can you translate the problem of finding all these possible extensions that come from a solution and relate them to some object that you can try to put in a computer and try to do a computation and see, okay, here they are or there are none of them. That is somehow the goal of all these projects. And if, for example, search conjectures were true in general for any totally real number field, then somehow that should be pretty much the end of the story, because then you know that this representation that you have constructed really comes from a modular form, and then you can try to go ahead and try to compute the spaces of modular forms and see what happens. And so such conjectures are only known over Q so far. I mean, it was proven by Carrier Wittenbescher in 2000 something, in 15 or something like this, or maybe a little earlier. But it's only proven over Q. It's not known for any other number field which is not a rationals. So we don't know why these forms are attached to modular forms at all. And so how do you solve this issue? And the idea of what Darmon proposed in his article is to try to construct global objects whose reduction is this rho synoptic. Okay? And what do I mean with a global object? Well, if you recall how we started with an elliptic curve. So when you have an elliptic curve, you have a representation over set P. So you have a representation, a characteristic 0, and the object you're searching for is its reduction modulo P. And so how would you like to know whether you have such an object in general? You have a global representation over something of characteristic 0, the ring of integers of a number field, or a completion of the ring of integers of a number field, such that when you reduce modulo the maximal ideal, you get the object that you were searching for. And so what Darmon did in his article was in some of the families. So for some of the lines, so Darmon constructed some curves of the form y squared or y to the n equals some particular polynomials that that gives you global representations. And what do I mean with lines? So remember that, so we're working on a three-dimensional space. We have Q, P, and R. My notation is a little different than what is usually used because I want to move the middle parameter, and I will explain why in a few minutes. So it's of dimension 3, and as I said, somehow when you want to apply the modular method, you can only move on lines. So somehow what you can do is like to move all the lines at the same time. So this is like the PPP exponents, which is Fermat. Or you can say, for example, I don't know, I want the first two lines to move the same and fix the third one. So then you have like families, which is like PPR. Or you can say, I want to fix two of the parameters. To be the same, and the other one to be free. So then you have like Q, PQ, or you can just fix X to be Q and Z to be R, and then you have like the family Q, P, R. So somehow like these are like all the 4 different lines that you can try to study with the modular method. It will only work for lines. So this is like classical Fermat, and these 2 cases are the 2 cases that were somehow considered by Darmon. And this case is a little harder because it's harder to give a curve that has these global representations. And somehow what I'd like to try to convince you using hypergeometric motives, which is somehow the title of this talk, how you can try to achieve that. Okay, so just this was like a quite fast introduction of, I don't know, 200 years of number theory. And I really want to talk about something which I try to explain in a little more detail to try to achieve this goal. So I want to talk a little bit about hypergeometric motives. Okay, so where do these hypergeometric motives start from? So they start from this hypergeometric series. So choose 3 numbers and just define formally this infinite product. Where this notation is the Mohammed symbol. This is A times A plus 1 times A plus N minus 1. Okay? It's just a sum. It's not hard to see that the sum actually is a function, it converges. And so how this sum was studied from different perspectives. It satisfies a differential equation, a degree 2 differential equation. But it also, the hypergeometric sum, so this is the hypergeometric sum, which was mostly studied by Gauss. It has an integral representation, which can be given as the product gamma of B divided by gamma of A, gamma of B minus A, It's not that important, the constant, but it plays a role. X to the a minus 1, 1 minus x to the b minus a minus 1, y minus z x to the minus c dx. Okay? So here what you have to keep in mind is two different things. This part here is just the quotient of gamma functions. And this part here is an integral of a differential form on a curve. So what is the curve behind? So I'm going to suppose that the three integers, a, b, and c, are rational. I'm going to denote by n their least common denominator. Then if you consider the curve, which is given by y to the n equals x to the n times a minus 1 times 1 minus x to the n times b minus a minus 1 times 1 minus zx times minus nc, then what you're computing in here is what is called a period of this curve. Because it's like you do with elliptic curves, right? I mean, you take the differential form and an automorphic differential form, like dy dx over y, and then you just compute the integral, and then you can take the nth root to define your variable y, and then you get like the elliptic integrals that you do when you compute with modular forms, right? And when you take the nth roots, you just recover the exponents that appear on the right-hand side. And so when you have something like this, you're computing a period of an elliptic curve, then this equality is telling you something about some algebraic structures in behind. So in this case, it's telling you that there should be some motives that gives you a relation between the left-hand side, which is the hypergeometric sum, and the right-hand side, which is a product of two different things. One thing, which is like the motive coming from the elliptic curve, and another thing, which is a quotient of gamma functions, which is a Jacobi mode. So it's something which has that dimension 0. And so how this is a just a motivation for the hypergeometric motive that you want to define in behind. And what I say is that when you choose four numbers, so let A, B, C, D be two pairs of rational numbers, and let n to be the least common denominator. Okay, so my claim is the follow. Okay. So now for me, an hypergeometric motive is only going to be a pair of two rational numbers. Okay. I want to state some of the properties that you can get out of it. So some facts. From these rational numbers, I'm going to define three matrices, M0, M1, and M-infinity. It's going to be defined in the following way. So the second pair of coordinates is going to give you the matrix at 0. The first is going to give you the matrix at infinity. So I'm going to define it as e to the c, e to the d, 0, 0. If c minus d is not an integer. And a Jordan block if C minus D is an integer. I'm going to define similarly the matrix at infinity, minus A minus B, if A minus B is not an integer, and A to the minus A, 1, 0, E to the minus A, if A minus B is an integer, and at last the matrix at 1, I'm going to define it to be 1, E to the A plus B minus C minus D, if the sum is not an integer. I'm going to define it to be 1, 1, 0, 1, if it is. Okay, so this is just a formula. I'm just here defining three matrices, what I'm calling M0, M1, and M infinity. What happened? Okay. I'm just defining three matrices. And what does these matrices have to do? On the one hand, so these are the monodromy matrices. Monodromy of the differential equation. Okay, I'm not talking about the differential equation, but this is where they come from. So the function satisfies a differential equation, which is of the form z times z minus 1, and then you have to take the second derivative with respect to z. So you have some issues at 0 and 1. And every time you have a differential equation, you just can attach to it a monodromy representation. But this is something which is somehow of a complex nature. Okay, so from the differential equation, you can define these matrices. And what is somehow miraculously is that, okay, then there exists some theorem. There exists a motive, an hypergeometric motive, defined over Q of Z and H, satisfying. I'm going to define H in a second. So the first condition, I'm just going to talk about its specialization at a point Z naught in Q, which is not 0 or 1, is unramified outside the sets. I'm going to define a set of bad primes, which are going to call tamely wild, which are just the primes dividing n. A set which is tamely, potentially wild, potentially tame, which is just the primes such that the evaluation at P of Z naught is not 0, together with the evaluation of primes such that the evaluation of P of Z naught minus 1 is not 0, and is not the potentially wild. So let me just give you an example of what am I saying. So suppose you want to understand the Fermat equation with exponents Q, P, R. Okay? So P is going to be the variable which is moving, and P and Q are the fixed parameters. For example, let's say I want to understand the 3P, 5P3. So I want to construct a motive for which the wild primes are going to be 5 and 3. These are the primes where I don't have any control. Okay, but that's okay, because these somehow have to do with exponents. They don't have to do with any solution whatsoever. They only have to do with exponents. And then when I specialize, there are going to be some bad primes, which has to do like exactly as happened in the case of the Frey elliptic curve. When you specialize Frey elliptic curve in the beginning of the talk, if you specialize here, for example, at 3, and then you look at it mod 3, this number here is going to 0, so you're going to have bad reduction at these primes. So these are the primes that are bad primes, but because of the specialization, not because of the motive. So somehow you have some primes which are bad because of the motive, and some primes which are bad because of the specialization. And this is the difference between the tame and the wild primes. So the tame primes are the ones that have to do with the specialization, while the wild primes are the ones which has to do with how you choose the parameters. Okay? And what is somehow miraculously is that if P is tame or potentially tame, well, I'm not going to call it P, let's call it L. And then you want to understand the image of inertia at L globally, then this is exactly the matrix MI evaluated to raised to the evaluation at L of the specialization. Okay, let me write it like this. AI, where if specialization is congruent to 0 modulo L, you see, somehow we're searching for extensions of P1 which are ramified outside 0, 1, and infinity. Okay? And so if my specialization goes to 0, I'm going to have to look at the matrix at 0. If the specialization goes to 1, I'm going to have to look at the matrix at 1. And if specialization goes to infinity, I'm going to have to look at the matrix at infinity. So when you start with the rational numbers and you look at modulo L, then it might be the case that it gives you 0, 1, or infinity. So if it gives you 0, then you have to look at the matrix M0, and you have to look at the evaluation of the parameter. If the specialization gives you 1, then you have to look at the matrix at 1, and you have to look at the evaluation of the parameter -1. So what's the order? If the specialization gives you infinity, so it means that it's in the denominator, then you have to look at the infinity matrix, and you have to raise to the minus valuation. So let's go back to the example. Suppose you want to understand the equation with exponents 5, P, 3. Okay? So my specialization is going to be in a solution which is of this form. So a to the 5th C cubed. And so I'm going to choose the rational numbers to be 1/3 minus 1/3, 1/5 minus 1/5. Why is that? Because in this case, this guy here is telling me that the matrix at 0 is going to be a 5th roots of unity. And if I have a prime which divides the value of A, then zeta 0 is congruent to 0 modulo L. But then the inertia is just going to be generated by this matrix M0 raised to the evaluation at L of A to the 5th over C cubed, which is divisible by 5. You see here you have a 5th power. A is separated to the 5th power. But when you do M0 to the 5th power, it's just the identity. So you're killing the ramification. So you're using the fact that your solution has a 5th power in the numerator to kill the ramification of the mononormy matrices. And so what happens is that if you consider this motive and you specialize in a solution like this, then globally, so the fact is that the motive with parameters 1/3 minus 1/3, 1/5 minus 1/5, when you specialize at the end at the solution, globally, it is unramified outside the primes 3, the primes 5, and the primes dividing the value B. And the reason why you have the primes dividing the value B is because when you compute the sum of these two numbers and these two numbers, it's going to give you 0. And so in this case, our matrix and infinity the matrix M1, it gives you a matrix of infinite order. So what happens is, in this case, the problem is that the M1 is the matrix 1, 1, 0, 1, which has infinite order. And this is exactly this matrix is the multiplicative reduction case of an elliptic curve. So this matrix has infinite order, that's okay. But the point is that when you look at the mod P Galois representation, is unramified at the primes dividing B. And the reason is 1, 1, 0, 1 to the P is 1P 0, 1, which is congruent to 1, 0, 0, 1 modulo P. I mean, believe it or not, this stupid computation is somehow the reason why you can, when you want to construct a global representation, so ideally, you like to get something which is of order, as Darmon was studying, something which is of order P, Q, and R. You like to have a matrix of order Q, P, and R, but you cannot do that. So what you do is globally, you replace the P by a matrix of infinite order. And the point is that the matrix of infinite order is going to be a matrix such that when you raise to the pth power and you reduce modulo P, it's going to become also the identity. And so in this sense, in this case, what you are able to get is you're able to construct, using these hypergeometric motifs, to construct global representations, in any case, which have somehow the expected properties that you'd like, in the sense that they don't have globally the ramification you search for, because the primes dividing B are going to be also ramified primes. But when you reduce the modulo P, they're going to be ramified. And this is somehow as best the best you can expect, that you can aim for, to have something which has very little ramification, but not globally. But when you reduce modulo P, you're really losing a lot of ramifications. And I just want to mention two other important features of these representations, of these motifs, which is the following. So the first one is that the trace of Frobenius at good primes is easy to compute. And this might look like a naive comment, but in general, this is extremely hard if you have a modular form to try to compute its APs, for example. And here you have a finite version of the Hypergeometric series, such that if you give me the A, B, C, D rational numbers, you give me a specialization and you give me a prime, it gives you as an output the value of the Fourier coefficient. Okay, and this is actually implemented by Fernando Rodriguez Villegas. So this implementation in Paris by Fernando Rodriguez Villegas. And another very important feature is the following, is that they satisfy many congruencies. And this is also a key important feature for this theory. And I don't want to take too much time, I just want to explain in the example what are these congruencies and why they are important. So let's suppose that you want to understand the equation solutions of the equations x to the q plus y to the p plus z to the r equals 0. Okay, where p is the variable, so q and r are fixed and p varies. And what I say is that consider, as I was saying before, consider the motive, which is 1 over r minus 1 over r, 1 over q minus 1 over q, and specialize at the value, start with the solution, a to the q over c to the r, and try to see that it cannot exist. And then you say, okay, but how can I even try to relate it to anything at all? So first of all, I would like to know whether is this modular? Because if it comes from a modular form, they can say, okay, maybe I can try to go and try to search something in some particular spaces of modular forms. And the point is that there is a congruence modulo R, and this is a little bit of abuse of notation, but it doesn't matter. So there is a congruence between this motive and the motive 1 over q, sorry, write it the opposite way, 1 over q minus 1 over q specialized at the same point. So the sort of congruences that they satisfy is that if you look at a congruence modulo a prime, somehow you can erase things that are 1 divided powers of this prime. And this holds in general. This is just a very easy result. And the reason, somehow the underlying reason, is that an nth root of unity is congruent to 1 modulo a prime dividing R. This is all the proof is this easy result. And the thing is that how can you try to use this sort of congruences? Well, you can try to use this sort of congruences because this is one of the curves studied by Darmon, for example. And this is something that played a huge role in number theory during many years. When you have congruences, you can also try to prove modularity. Why? Let's suppose that you know that this is modular. Then, through a congruence, you have some strong results due to Wise and many collaborators, Taylor-Wise, and many more sophisticated versions, which tells you that every time you have a congruence, when one of the objects is modular, when one of the objects is related to a modular form, the other one is also related to a modular form. So this is some principle called like propagation of modularity. And the fact is that the motifs has a lot of such congruences. So in many instances, you can actually prove that many of these motifs are actually modular. And then in particular, knowing that it's modular, it says that it comes from a modular form. And so, for example, these motifs here are modular if R and Q are larger than 3, are different. Then you do have modularity, and then you can go ahead and try to compute a particular space of modular forms where these things appear. There are some issues. So this is an ongoing project with Lucas Vichagra. For example, what happens if you say, okay, then can you solve this equation? There's some issues. The spaces that you need to compute, and a big issue. So there are two issues. And I finish here. One is computation. For example, in this case, for this particular equation, one of the spaces that you have to compute has 2025 as its dimension. You may think, well, 2025 is not that large, but you have to try to diagonalize a matrix which has 2000 entries. That's pretty much in the border of what we can do, but it's only one of the spaces. If you want to compute all of them, then some of them are even larger. So if you want to study, I don't know, 7p3 or 7p5, then the spaces are going to have dimension too large for nowadays computations. So this is a big issue because you're saying, okay, I solved the theoretical problem, but now I cannot prove anything because the computer doesn't stop. I mean, it never ends. So this is a big issue, okay? So this is one of the issues. And there is another issue which somehow was unattended. It's like the existence of non-solutions is an issue. And let me just say what a non-solution is. Suppose that you go back to Fermat's original problem. And what we said is that from a solution ABC, we substitute in minus a to the p divided by c to the p, and this gives an extension with very little ramification. Okay? And now my point is that what happens if you consider the equation which is not the same, but is you just put like 2 to the x. Okay? It has nothing to do with the original extension equation. Nothing at all. But this has a trivial solution, which is like 1, 1, 0. Put x equals to 1 and y equals to 1. And so how in the original situation, you would put like z equals to minus 2. And then this tells you that if you specialize the original curve, Euler's curve, phrase curve, at the point minus a half, this is going to give you an extension which has very little ramification. It only ramifies at 2. There is no prime bothering you except 2. So this is also something which has very little ramification. It doesn't come from the solution because this equation has nothing to do with this other equation. But in the end, the only thing that you strongly used, is that you have only very little ramification. So these sort of non-solutions, like coming from this equation, are going to hit some particular modular forms that you will not be able to discard at all. And so what happened in the original case is that in the Fermat case, you can flip the coordinates A, B, and C, and you can say, oh, I'm going to assume that B is even, and then I only have one space, which is 2 to the first power. Because this corresponds to a CM elliptic curve whose conductor, I think it's 64, if I'm not mistaken. So it will be in one of the spaces that you cannot discard. And this, when you work with the general equation, you cannot do any trick on the permutations, so you're completely screwed. So these sort of big issues, also we still don't know how to solve. And when we can prove some conditional results, which says, for example, if A is divisible by 3, then in the particular case, the particular space where I cannot discard one of these forms, then I don't know how to do anything. But if A is divisible by 3, I don't have to consider this space, so I can prove non-existence of solutions. But I think that these are two different issues. The second one, I don't think it was ever explored or detected before, and it really appears in these cases. And this already was known before, that we are really reaching like the computational boundary where we can really still do some computations. So I don't know if I probably that's what I would say. I can take some questions.
So thank you very much for this nice talk. It was really exciting. So are there any questions or remarks? I have a question. Which computer program are you using for these computations? Magma
Which
or
what?
which?
Okay. So that two different. That's a very good question. So okay. So it depends. You have to use all of them somehow. So let me explain you why. So when you want to compute with Hilbert modular forms, now here, for example, as I was saying, why do we consider the exponent 3, 5p? So 5p3, there's a big explanation here, because in this case, you have to consider this field, which is just q square root of 5. Okay, so it's quadratic. Okay, the larger the exponents, also the larger the field. So the complexity of computing the spaces of modular forms depends on the degree of your base field, because it's the norm of the ideal. So if you have the ideal 2 and the degree is 10, then the norm is 2 to the 10. So somehow the complexity depends on the degree of your base field. So for computing with Hilbert modular forms, you really have to use Magma. I mean, there is some implementations in Sage, but they're really slow. So since these matrices are huge, you really need to use Magma to compute the spaces of modular forms. Okay? Now, once you compute the spaces of modular forms, then if this is not the case, and it's already happening in the literature many times in the literature, that the spaces are empty. Of course, there are a lot of forms there. And now you like to try to discard forms as not being related to solutions. And this is something that we don't know exactly how to do. There are some ideas due to Meso that somehow works in quite a generality. And this is where you have to really use this fact that I was saying here, that this fact here, that things, that the traces of Frobenius are easy to compute. And how does this method work? And I think it's a really nice idea. Suppose that you want to study solutions of this equation, and you say, I don't know how to solve this over the integers. That's exactly what I want to do. But what you can say, okay, what happens if you solve it modulo 5? Well, modulo 5 is a bad idea. Let's suppose you want to solve it modulo 7. Okay? And now modulo 7, you can't do it because it's finite, it's a finite computation. Okay? And you say, okay, now I try to solve it modulo 7, I compute all possible triples ABC, which are solutions modulo 7.
247, 3.
Okay? And now from this solution, I can take T0, which is exactly a to the 5th divided by c cubed. Okay? Now, any global solution has to reduce to a solution modulo 7. Right? Because you start with something which has integer coefficient, you reduce modulo 7, it has to give you a solution of this guy over here. And so but the key fact is that this guy here, you can compute it because we use the algorithm written by Villegas. And so this is give you a candidate for the A7 of the motive. So for each solution modulo 7, you compute this number T0 and you compute the A7 attached to this value ABC. Okay, and then you compare this value with the 7th eigenvalues of the spaces of given modular forms. If they don't match, the form doesn't come from a solution. And this is how you discard the forms that appear in the space because you're saying they're not related to solutions. And so you need to compute these values and see whether they match the ones coming from the given modular forms or not. So this computation, we're doing it in PariGP because the script written by Villegas is in PariGP. And the good thing somehow is that it doesn't depend on any equation of the motive. So the trace of Frobenius is just a sum of Gauss sums. So you can actually compute it in PariGP or many other softwares. It's written in Pari. But it doesn't depend on choosing an equation. That's somehow the advantage of working with these hypergeometric motifs. This is what you compute and try to compare to given modular forms.
Yeah, it's a little bit complicated process, actually.
Yeah, everything is a little complicated process, and still, in the end of the day, so most of the times you cannot prove many new results because of some of these two issues, right?
I see.
But
no, thank you very much.
Sure.
Any more questions or remarks? You have thank you message on the chat. So thank you very much again for accepting our invitation. It was a very nice talk.
Okay, thank you very much. I apologize for I thought that 50 minutes were more than what I
no, we are very happy about this. Informal talks are better than formal talks, so we are very happy.
No, I know, but you don't want to spend 2 hours talking when you're invited to give a 50-minute talk or something like this, so that's why.
Definitely no problem. So thank you very much to the speaker again, and see you next month. And next month's speaker will be Professor Ben Kane from University of Hong Kong. And he will speak about some topics on hopefully on modular forms. So thank you very much and see you next month. And see you, Ariel.
Okay. Thank you for the invitation.
Obrigado.
Bye.
Bye-bye.